Welcome back, students. In this video, we're going to continue to explore multi-electron atoms and term symbols. Specifically, this video is going to talk about Hund's rules. So you may or may not recall that once upon a time in general chemistry, we taught you that when you were filling electrons into orbitals, that if you had degenerate orbitals, like the set of 2p orbitals, you first put electrons in unpaired, all with the same spin, and then you went back and paired them with an electron of the opposing spin after all of the degenerate orbitals had at least one electron, which was kind of a funny rule. And you may or may not recall that we told you once upon a time that this was called Hund's rule, singular. Turns out that it's Hund's rules, and there's 3 of them, but they're going to give us the same result. And so Hund's rules, plural, are derived from atomic or molecular, but today atomic, term symbols. So let's think back to the system we were dealing with yesterday when we first encountered atomic term symbols, or Wednesday. So on Wednesday, you had 2 electrons that were filling the 3 different 2p orbitals, and you should have found the following term symbols for this system: a singlet D2, triplet P2, triplet P1, triplet P0, and singlet S0. If you didn't find those term symbols, you should pause the video and you should send me a message so that we can talk through that and figure out what happened. And it's okay if you didn't, right? You're learning them. Mistakes are part of learning. So, if you did get these term symbols, let's go ahead and start looking at them. Which one of these is the ground state? Which term symbol represents the lowest energy or ground state of the system? Is there a way that we can put them in order, such as putting them on an energy diagram? Can we say this one is the lowest energy, then that one, all the way up to the highest energy state? Turns out that Hund's rules is going to give us a systematic way of putting all of these in order from lowest energy to highest energy. So let's dive right in. Hund's first rule, and it's important that you do these in order, always do rule number 1 first. The first rule is that larger S values will have a lower energy. Where does the S value, or the total spin, show up in your term symbol? Multiplicity. Remember that superscripted number to the left of the letter is your multiplicity, which is equal to 2 times S plus 1. So the larger our multiplicity, the larger our original S value was, which tells us then that our triplet states have to be lower in energy than either of our singlet states. So the 3 triplet P's are lower in energy than the singlet D and singlet S. But other than that, we can't distinguish between them. We can only draw the line between the triplet and the singlet states based on this rule. So let's build on that a little bit and go on to rule number 2. Rule number 2 says that larger L values have lower energy. So we know that all 3 of our triplet P's are lower in energy. Where does the L value show up in your term symbol? The letter. So that capital letter in the middle represents your L value. So S represents L equals 0, P represents L equals 1, and D represents L equals 2. This is very similar to the lowercase s, p, and d that we call our hydrogen-like orbitals and their L values, right? Their lowercase L values. So capital L is going to mirror lowercase l in this case. And so we know that our triplet P's, all of them are P, so they all have L equals 1. So they are still lowest in energy, and we can't distinguish them apart. So the triplet P's are still all lumped together. We don't know which is lower in energy. But this does allow us to distinguish between the singlet D and the singlet S. Which one of those has the lower L value? D or S? S, so that has to be the higher energy. Remember, the largest L value has the lower energy. So this means that our triplet P's are lower in energy than our singlet D, which is lower in energy than our singlet S. So we're starting to get there. Now the only thing that isn't defined is our 3 different triplet P states. We still don't know which one of those is lowest in energy. So this is where rule number 3 is going to come into play. So rule number 3 states that if the subshell, which in this case is the 2p subshell, is less than half filled, then smaller J values will have lower energy. However, if the subshell is greater than half filled, then the larger J values will have the lower energy. So, quick note, if your subshell is perfectly half filled or perfectly filled, you will not have to apply Rule 3, right? You will always have a definite answer after Rule number 2 has been applied. So, if we think about our particular system, we have 2 electrons in 3 2p orbitals. Are we less than half filled or greater than half filled? So the 2p orbitals can fit 6 electrons. So if we only have 2 electrons, we're less than half filled. So we're going to be looking for smaller J values, and those are going to be the lower energy states. So if we look at our 3 triplet P's, they have different J values. Remember, the J is the Russell-Saunders coupling, and that is the subscripted number to the right of the letter. So this is going to tell us that our triplet P0 is going to be lower in energy than our triplet P1, which is going to be lower in energy than our triplet P2, which is going to be lower in energy than singlet D0, which is lower in energy than singlet S0. So we've put all of our term symbols, or all of our different states, in order from from lowest to highest energy at this point. So we could now build an energy diagram, which would say the same thing, right? We could put these in order. And we would know that the ground state, or the lowest energy state, should be that triplet P0. However, if we want to know how far apart or how close together different states are with respect to energy, then we would have to do a measurement. So remember, those types of measurements would be either photoelectron spectroscopy or UV visible spectroscopy. So, I told you at the beginning that the Hund's rule that you learned in general chemistry was that you put electrons in unpaired first. Let's see if that holds up with the Hund's rules that we just went through. So we were told that the triplet P0 is lowest in energy. So let's investigate what that means just a little bit. So if we draw our 3 different 2p orbitals with their respective m sub L values, -1, 0, and +1, we know that we have a p-type state here, a p atomic symbol, which corresponds to L being equal to 1. If L is 1, then our m sub L values that are possible are +1, 0, and -1, which means that our electrons aren't in the same orbital, right? We could technically get L equals 0, or m sub L equals 0 by putting both electrons in the 0 state, but we could only get L equals +1 or L equals -1 if the electrons are unpaired. So this L equals 1 represents unpaired electrons. So they are unpaired. All right? The S value also equals 1, which means that they have to have the same spin, because that means our possible m sub S values are either +1, 0, or -1. And again, we could get 0 by putting them in opposition to one another. But in order to get an m sub S of 1, we'd have to pair them both spin up, and an m sub S of -1, we'd have to pair them both spin down. So this means that the lowest energy state corresponds to the electrons being split up in 2 different orbitals, and both either spin up or both spin down. It actually doesn't tell us which spin up or spin down, and it turns out that we can't tell the difference between both being spin up and both being spin down energetically. So we accept this. This looks exactly like the Gen Chem rule we taught you once upon a time. Alright, so before we leave this video, I'd like to sum up some of the multi-electron atom rules that we've learned, because they've been scattered, with the exception of this one, as little side points in other videos. So if we think about all of our multi-electron rules, which you actually saw once upon a time in Gen Chem, but you may not remember that they had names. One was the off-bow principle, and that means we fill from the lowest energy state up. So if we're putting electrons into atomic or molecular orbitals, we always fill the lowest states first, or the lowest orbitals. So in general chemistry, this looked like putting electrons first into 1s, and then if you still have remaining electrons, filling the 2s, and if you still had remaining electrons, then you started putting them into the 2p. Our other rule that we learned the other day, I think this was on Monday's lesson, was the Pauli exclusion principle. And this states, the Gen Chem version is all electrons within an atom have to have a unique set of quantum numbers. The other version that we learned on Monday was that the wave function for a multi-electron atom must be anti-symmetric to the interchange of two electrons. And then the rule we learned today is Hund's rule, or the set of rules was Hund's rules, which tells us how to distinguish between different configurations of electrons within unfilled orbitals, and how to tell which is the ground state.